Thank you very much. Hello. Good morning, good afternoon to everybody, and with everything you've said about me, I don't need to introduce myself, I guess. So let's begin in order to have some time left for questions afterwards. So I'd like to give you a short introduction on Tempest. And we're going to be going to introduce everything that we have in this area. First of all, this is a technique that we know as a covert channel technique. It's a technique that we normally use. It's an evasion technique that we use in order to send information through legitimate channels that are not there for being used with certain users. For instance, we may send information in the TCP/IP headings in different data fields that are not normally used. But nevertheless, as regards Tempest, what can we say about taking and filtering information in an equipment without any sort of connection to anything? There's no Wi-Fi network, there's no Ethernet, there's no Bluetooth, there's nothing whatsoever. So can we actually take information we're interested in from it? For those of you who don't know Tempest, well, this is a spec of NSA, that is the bad guys, but this is no NATO under NATO certification. And through the leak of things that includes radio signals or the electromagnetic signals, and covers several methods, spying and also equipment protection in order to avoid these information leaks. This last part, this is security of emissions, and these methods, for instance, these NSA methods, here we may be good or bad guys. All this is classified, and here we have the protection standards that sometimes are published by NSA or the Defense Department, and they speak about the distance from equipment to the war, for instance, things that we hadn't been paying attention to so far. But it's something we can see in the industrial area, and in this case, these things are contemplated. Here, manufacturers strengthen chips, they armor chips with filters, armoring, etc. And what is happening here with all this? Most of us who, well, here we have everything related to the leak of electromagnetic emanations and in cell phones, etc. Here we can discover certain patterns and with different sensors, and all these leaks are analyzed, and this is information that can be processed by any equipment. So starting from this, what we do is have a Tempest attack on any electronic device that will emit electromagnetic radiations. Every time there's a small electrical current will generate electromagnetic pulses that will be radiated as invisible radio waves. They're invisible, but they are there. And CPU is emitting, and we can amplify these signals. We can send certain things to the CPU in order to try and modulate certain signals we're interested in. So under these schemes, we can see the normal boards, and we see that everything is radiating, and the idea is to send information in order to reach our goals. We must also say that this is a passive sort of attack, something that cannot be detected because we don't attach anything to the equipment. It is our own equipment that is in danger, and here we wouldn't be able to detect somebody in the street with an equipment, somebody looking for our CPU or the LEDs of our card or whatever, and if we get too paranoid, we'd arrive to this, come to this situation. So is this reality? And we realized that this started in many years ago. And so a message was sent with respect to the fact that signals could be taken and modulated, simple codes, etc., with using old monitors, old screens. We could take a song and it could be received in a normal radio. We have projects in order to use this with FM, and this is from 2016, and here we can filter data through, for instance, certain systems, right from fans or ventilators or certain mechanical parts in the hard disk with noises. And for instance, and we have this example here through a receiver, an SDI, for instance. This is a software-defined radio, and here we can spy a screen where there is text, and this is reproduced without any problem. And this is a recent test with another sort of device, and we can see that it is reproduced without any problem. And one needs to be very close to the screen, but with some sort of aerial or antenna. We see somebody in front of our house, for instance, who's doing this to us. And here we come to the revolution, and here the target has to do with using something legitimate that cannot be cancelled out. Sometimes there may be critical systems, and somebody comes with a USB and updates it, and so this is for very specific operations, and the idea is to provoke an intentioned leak, information leak. And then we have the system bus radio, and here, as you will see, we have, here we see where everything starts, and the how. Well, the idea was to run legitimate instructions in an equipment that will cause electromagnetic radiations by the noise that is generated. Here we have the development part, where we are given a series of instructions. Here, manage data from the CPU to memory, from memory to CPU, in order to write or read or whatever. And what are we doing here? Well, we simply send zeros and ones, but within a series of timers and very quick things in order to try and get signals. And another target is to send information through radio carrying wave, the modulated amplitude, this wave that may vary. And here we have the bus, the CPU, our antenna, everything's integrated. And this comes from the original project. So here we have these signals we want to transmit, the carriers and the time. And here we can start doing things. So I'm not going to go in details here because this is something that's already been presented. Old equipment that transmitted signals through Morse. But the thing is that this takes time. And apart from this, all this is based on very low frequencies. Somebody who has an FM receiver, for instance, you switch it to AM and you leave out a whole set of frequencies, and here you can go up and down and play around a series of things, and you can do this much better. Here you can modulate things that allow for more speed, preserving the integrity of all the information that's received. And here we see the different problems we have with Morse code, difference between dot or line, or new characters between the different things. When we begin, when we end, message, whatever. So that was a bit of a problem. So what could we do based on series of frequencies and hertz? We could do many things. We could say, well, I'm going to each of the characters that I'm going to transmit, I'm going to assign something to them, or I'm going to try and make sure that this will beep, and once it beeps, will this is the main routine. This doesn't change, hasn't changed with respect to the original project. These are instructions with a stream, and here we send 1 and 2 zeros, and we send it quickly, and we know when it falls. And here we have the zeros, the ones that we are taking and sending, and the formula is quite straightforward, very easy. And if we want it to beep here when we receive the signal, we can take it, and I'm not going to go into signal theory. The signals we receive, maybe, I don't know, some things that maybe are not necessary. So now we go to the first demo, and let's see if it works.
Sí, me activan. Ahora sí que necesitaría por aquí esto que tengo en la mano.
Okay, this I have in my hand is a radio set. Bought it from Chinese. On a Chinese store.
Ya no se lleva, vamos y compramos todo completamente digital y no lo tenemos. Y bueno, yo lo único, pues no sé si
I turn it on. I don't know if you can hear it.
voy a ponerlo, a ver si lo puedo poner aquí mismo. Vamos. Bueno, os voy a enseñar simplemente lo que es pues un poco el código.
Bien.
Y
And now I'll show you the code, and here's the routine and a series of sounds. And here we just to see whether this can reproduce these sounds.
Compilamos y vamos a ver si somos capaces de...
We compile and we'll see whether we can reproduce this. Let's see if we can take it out and if we can extract it. You hear it? Yes?
Este se lo queréis quitar ya. Bueno, habéis visto que se recibe.
As you can see, receive sounds, no problem, so we can just play around with the sounds part. So, and this is where things start getting more complex, where this beeps. We can receive it remotely. Now we can start talking about symbols, modulations, and the bit rate that we can achieve, codes, gray codes, everything else, and maybe one sound after another in order not to have any problems when receiving problems for receiving these sounds. So we've run several tests, and the first thing we had to decide was to, for instance, simulate and here we want to do is to simulate 16 QAM. So this, the idea is for this to let us send more information, so we can assign a whole table and transmit 4 bits with 16 keys, 16 notes. So, for instance, with gray code, in order not to repeat, in order to have 1 bit variation, so that we may be able to do it. So here we've chosen a series of notes with a given duration, and I wanted to try this out and see if we could hear this, whether we couldn't hear it, and yeah, more or less what you will hear around each note, 250 milliseconds. That's how much they last, and then there's a gap of 50 milliseconds between notes, in between notes. We want to see whether the receiver can decode this, but we'll be able to hear it and we won't be able to tell.
Es exactamente igual que el otro.
Exactly the same as the other one. But
aquí más o menos lo digo porque me lo voy a saltar, pues un poco por falta de tiempo.
I'm going to skip this because we don't have enough time, but these are the results of different tests. Those of you who know musical notes know that there's a series of frequencies, and of course, depending on how well you can hear it, some of these notes you can hear, others you don't. For instance, we play a note and for some time, and you can hear these, or you can tell there are some micro cuts. Macro interruptions. Here we have 16 ones with a code. We have a character, X character, LSB, LSD, on according to the bits and the notes corresponding to this. And in order to hear it all, let's compile this and let's take a look at it.
Y vamos a ello. Perdón. Es que como no se ve. Y ahora sí que necesitaría otra vez, antes de darle. Sí. Mirad, lo pongo así, por aquí lo...
I don't know if you can hear it. Can you hear it? Just to show you duration, to see what we could do. So what we do is to listen to a sound, a receiver. For instance, I can hear notes, see whatever, with a given duration. No problem. So starting from this, we have this massy table, and what we did was what I told you, the MSD, the LSB, we divided into hexadecimal, and what we want to do is to be able to transmit this MSB, LSB, etc. And we this into the 50 milliseconds. In order to transmit the MSB and LSB, what we did was to define a 50 millisecond gap. So in order to transmit each bit, we would need, of course, including gaps, we would need 12 slots. This is around 500 microseconds per character. So obviously we'd be speaking of rates around 1,000 bits per second. I don't know if you remember old routers or modems. We're speaking about ridiculous speeds. Nothing. Of course, we could never imagine that in a normal house we could achieve a sort of transmission we achieve now. Of course, with compression and everything else, even though I'm not speaking about compressing data, I'm just speaking about the part of the project, things that can be seen. And just to show you what we can take and what we can do with it.
Imaginaros, ¿vale? Imaginaros que tenemos, pues.
So, for instance, if I want to transmit this file, it's a very small file. I don't want to take up too much time with this, but so I can just create some routine.
Eso para que veáis que no tiene más, ¿vale? Que son simplemente...
Very simple.
Bueno, 4. Lo de 16 valores.
16 values, and here we define the gap, the main routine, the logo, of course, and just to show you what we're going to take, what we're going to send, and what corresponds to each character. So obviously there's no problem with this.
Compilamos y vamos a poner
You compile this.
también para que lo sigamos. Ahora sí que necesitaría pues otra vez a ver cómo todo. Lo mismo si estoy arreglando los oídos. Bueno, ahora cuando le dé, lo vamos a ir viendo
Now
letra a letra y carácter por
we're going to see letter per letter, character per character. And this is something you wouldn't see in a normal Tempest.
Bueno, si lo quitáis. Bueno, supongo que habréis visto los altibajos que tienen las notas, ¿no?
You can see how the notes go up and down, probably. Well, what can we say here? Maybe an AP starts transmitting for about 250 milliseconds, 440 notes, then it goes to wrap, then it transmits the next one, then the O, then the space or any of the characters. And then logically, at the reception phase, we can take that audio file we receive, and we can fine-tune a little bit more so that we can receive a perfect sound. And with the Python, we can do several things in order to receive what we've just gotten. Well, problems and solutions, troubleshooting. Well, the problem can be a broadcast transmission. Anyone who's in the same frequency is listening, and there's nothing we can do about it. Well, we can play a song they like and hide the notes behind the song that this person likes. We could cryptanalyze the frequency, and we can also have problems with binary files. If you have to transmit ASCII or, well, that's okay, from 0 to 127, but if we use all the things, or if I want to introduce the end of a file, for example, that would be a problem. And that is even a bigger problem if the number of characters is limited. And this is how the real Tempest works. First of all, there is an encoding. We extract a public key in RSA, and with that we generate an IV in order to take the files away. And what we do next is to code by files with an AES-256 CBC mode. That's important, and what we do is take in everything from that file, and from that we generate a binary file that would lead us to the next step, which is, once everything else is done, we encode the IV with the public key with an RSA 4096 in order to store it, because otherwise, when it's in the receiver, I won't be able to revert that symmetric. So who's going to have the private key? Well, the one who created the Tempest. So this person is the only one who can extract that public key and receive it. And the same goes for the next files. Then there is another problem related to coding. What about the coding? As you can see here, this is something that we've used on 64 base. We've transformed everything into 64 base. We could have used the encode or something that allows us to transform a binary file into a set of characters that I'm going to be able to receive. More problems. Well, if we are on base 64 and if we encode that, we may have difficulties in telling a capital A from a lowercase a, because this is something that you're going to have in 64 base. So what do we do in this case? Well, a replacement, a standardization, and this entails replacing the characters we don't like for other characters. For example, if we have to change from uppercase to lowercase, we insert 2 points and change the character. For example, a plus sign can be replaced by a minus sign, or a space between files can be replaced by an apostrophe. So this allows us to transmit, to broadcast through all the frequencies these characters that were a little bit troublesome in the beginning. When it comes to reception, that's a question that a lot of people ask. This is a very simple thing. I think it is the transmission part that is the tricky one, but still, the one who wants to receive this just needs to have this WAP recorded, and I'm talking about Python here, but we could be talking about other things. So all we have to do is take this package, get rid of everything that is unuseful, determine what is useful and what it corresponds with, and then the machine is going to do it itself, and the transformation is going to take place. Here is when you find out that this kind of programs are really useful. Now I'm going to go down to the next demo. This is a big fail. This is about a big fail that has been pretty recent. I'm sure you've heard of it. And it was the root without password. It's an epic fail. So what can we do about this? How can we do whatever we want with the root without a password? I'm showing this for OS X, but this is the same for Windows or for Linux. All of us using Intel are subject to this kind of thing. Otherwise, we can put this inside the fridge or something like that. So one thing we came up with was thinking, well, where are the cool things? Well, it is usually in the keychain. So what do? We take the keychain and we store it somewhere else, but there is a problem. For all the cloud data, etc., that's impossible. We cannot copy this. However, we can take some things away from other places. For this demo, I've worked a little bit harder. I'm going to erase this. And this is what I'm going to do. This way we can see a little bit what I'm about to do. Imagine I'm going to focus really to the important things. I'm going to native commands, and what I do is taking away the keychains. I take away all the things, not ADO files, for example, not shadow files. So if you look at the top here, the authorization is denied, the permission is denied. If I try with my user, it is denied. Imagine we've introduced this bug into an equipment. Well, the permission is denied, of course. So with this script, we just have to use what is on top, and in this case, we've taken nodes, DS local, default, users, and plist. So it's been able to gain access. And now, for example, I can think about creating in the TMP a file with hashes.zip. So with this all, I've added everything from the keychain. So here I have this file. Here you can see there's nothing. So what I have in the end is this file in the TMP that is called hashes. And now I say to Tempest, I want to transmit that file with that text inside, and since this is something that we don't usually automatize, we create a new Tempest, and the Tempest by itself generates this, and then I change it if I want. If you know how Morse works, you can see that this is pretty straightforward. This is a description, CyberCamp A17, for example, that'll do. And here, the file that I want to take away, it's a file named hashes.zip. So this is a binary that is going to be run with the rights that the user has. Sometimes we tend to think that the user is the administrator and that it has a lot of rights in the machine, but in many cases it isn't so, and we need to elevate the rights. So we can introduce a small exploit in order to elevate the privileges. I didn't have time in this case to elevate this part of the root, so I did it by hand. So with the OSA script, I just get what I'm interested in, that is the user. So in this case, I can turn it into polymorphic and generate this Tempest. And now what I can see are the characteristics, the binaries. As a matter of fact, I'm going to download the binary, the decoder also, because otherwise the demo wouldn't make a lot of sense. And here I have the source code. And if we take a closer look, we can see it's basically the same thing with a few more stuff included. It's not really complicated. The code is quite straightforward, as I say. And here we can see the key. We have the opportunity to continue transmitting in Morse, and it's not excessively complex. So having said this, what do we need to do next? That easy. We need to run the Tempest here in the demo. So this file stands for the Tempest that we created. And this is the one it corresponds to. I'm going to grant rights, and what we're going to do next in the machine is this. We would use the receiver to listen. We would use our wire and we would generate the file. I don't know if you can hear it.
¿Qué dice eso que podamos escuchar? Esto va a una velocidad.
So, what does this tell you? This goes at a programmed space that enables us to see the different leaps. We can run it at a faster speed if we want to. That's up to you and up to your choice. And here you can just make up anything you want. So now, next step would be to process an audio file that we've gotten and received with everything. So now, once the file has been processed, we have a file that we can see here. And if you remember what I said about replacements and the colon, for example, here we can see an apostrophe on the 7th or 10th line that indicates where the lockers are. That's the Morse part of the Tempest. This could be, of course, automatized, and that's what we would like to do in the part of the receiver. What do we have in the receiver part? Well, if everything is okay, now it can take and process. It takes a while because the file is pretty long, but what we end up having is a file which has been able to have the attacker. It's saying that this is a binary file. I'm going to say that it's not. This file, for instance, if we look at it, when I compressed it, it became a zip file. So, since the attacker is aware of that, all I have to do is decompress, and taking advantage of the bug, we get a library, we get a keychain, and we get the system keychain without a lot of trouble. Well, more interesting things inside the bar, the default, the users. Inside we have this. This is binary, but they include my hash because I stole it from myself. So in the day we can see the root .pist, and when we open and look, we get all the passwords and everything we want. So this could actually be useful in order to filter out the information we need inside that machine. So this was all. Thank you very much for your attendance. We have some time for Q&A. Well, if there are no further questions, next one is on you, Javi. Thank you very much.